Algorithm analysis is a fundamental aspect of computer science that can significantly impact how we design and implement software. At its core, it's about understanding how algorithms perform, particularly in terms of time and space complexity. This is where Big O notation comes into play. Big O notation provides a high-level understanding of an algorithm's efficiency by describing its performance in relation to the size of the input data. Imagine you're sorting a list of names. If you have 10 names, a simple sorting algorithm might work just fine. But what happens when you scale that up to 1,000 names or even 1,000,000? This is where understanding the time complexity becomes crucial. Let's break it down. Time complexity measures how the runtime of an algorithm increases as the input size grows. For instance, an algorithm with a time complexity of O(n) means that if you double the input size, the time it takes to run the algorithm also roughly doubles. On the other hand, an algorithm with a time complexity of O(2) will see its runtime increase exponentially as the input size grows. This is why we often prefer algorithms with lower time complexities, especially for large data sets. Now, let's talk about space complexity. This refers to the amount of memory an algorithm uses relative to the input size. An algorithm that requires a lot of extra space can be inefficient, even if it runs quickly. For example, if you're using a sorting algorithm that requires additional arrays to hold data, you need to consider how that impacts overall performance. When we categorize algorithms based on their efficiency, we often look at common sorting algorithms like bubble sort, merge sort, and quick sort. Bubble sort, while easy to understand, has a time complexity of O(n)2, making it impractical for large data sets. In contrast, merge sort operates at O(n) log n, which is much more efficient for larger inputs. Understanding these differences is essential for selecting the right algorithm for your needs. Real-world analogies can help clarify these concepts. Think of algorithm analysis like planning a road trip. If you know the distance and the speed limit, you can estimate how long it will take to reach your destination. Similarly, understanding the time and space complexity of an algorithm allows you to predict how it will perform under different conditions. Ultimately, grasping algorithm complexity is vital for optimizing performance and managing computational costs. It's not just about making things work, it's about making them work efficiently. As technology continues to evolve, the ability to analyze and choose the right algorithms will remain a critical skill in the toolkit of any computer scientist or software engineer. In summary, algorithm analysis, particularly through the lens of Big O notation, empowers us to make informed decisions about the algorithms we choose. By understanding time and space complexity, we can optimize our solutions, ensuring they are not only effective but also efficient. So, dive deeper into these concepts, experiment with different algorithms, and see how they perform in various scenarios. The more you engage with this material, the better equipped you'll be to tackle complex computational challenges.